Hi, friends. You're welcome once again to our class, and I believe you are doing fine. So, all this while we have been talking about electrolysis of this, electrolysis of that, and in our last class, we ended electrolysis. In one of the classes, we ended electrolysis, and today we are going into electrochemical cells. Remember also that electrolysis is a cell. Electrochemical cell also exists. So these two cells, they are not the same. In the course of all these classes, we will differentiate them. You will see the difference. And without wasting time, in electrolysis, we were using electric current from battery. We were using electric current to produce chemical substances. But in electrochemical cell, we will be using chemical substances to produce electric current. So watch carefully, if not, you will miss out along the line. Electrochemical cell, before I deep into it, I will start by telling you something about cell notation. Cell notation simply means writing a short way, a short method of writing something, which stands for a very long process. Now, for example, I said here that cell notation is a short method of expressing a certain reaction in an electrochemical cell. Short way of expressing a chemical reaction in an electrochemical cell. For example, this is a cell notation. This thing that you're seeing, this one line something you're seeing, stands for the whole of this drawing. Everything you're seeing here. Now, this is an electrode. This electrode is this one. This is a solution, which is the solution that you dip the electrode. This you are seeing is the concentration of this salt in this solution. I am trying to explain interpretation of this. Now, you move down to the single bar you are seeing stands for interface. If you carry a rod, put inside water, the boundary between the rod and the water, that's what single bar here. Now, the double bar here stands for this salt bridge. This is a different container, this is a different container, connecting something. Just like when you meet a river, for you to continue your journey, you have to pass through a bridge that connects this side to the other side. So this is salt bridge, connecting the solution to this solution, and it is represented with double bar. They can give you equation like this and ask you some question. What is double bar stand for? What is single bar for? Now, this side is, this particular one is the solution, the concentration, the plate. So you connect the wire into voltmeter. If you check, there is no battery connected into it. Solution connect the wires through their electrodes into voltmeter, and then put your salt bridge. You will see the meter, the pin on the meter moving either to right or to left. It will move, meaning that there's a flow of current generated from the two half cells. So this drawing all these and labeling all these, somebody has finished it with this simple term. And you also need to know that this is where oxidation takes place, which is this half cell. This is where reduction takes place, which is this half cell. And in the side of the oxidation, you can never write, if you write the solution before the electrode, you are wrong. So you always write electrode, this is electrode, as I told you, before the solution. But in the side of reduction, solution comes first before the plate. Note all these. I have interpreted the cell notation: single bar, change in state or boundary or interface between solid and liquid. Double bars, the junction between the two half cells, that is salt bridge. I've explained that. 1.0 molar solution, concentration of aqueous solution, the concentration. The whole of this is what? Oxidation, where oxidation takes place. The whole of this is where reduction takes place. Because if this ionizes, it goes into solution. If this takes electrons, it becomes the plate. So that's what happens here. So when you finish the connection, where oxidation takes place, which is anode, remember also that in electrochemical cell, anode is always what? Negative. Before, in electrolysis, anode was what? Positive. Cathode was what? Negative. But in electrochemical cell, anode is what? Negative. Cathode is what? Positive. Now, oxidation, in the two cases, oxidation takes place at the anode, reduction takes place at the cathode. Now, looking at this, oxidation takes place, it ionizes, the atoms on the surface ionizes and go to solution while the electron flows up and then return to this side. Now you can see that oxidation, as it is ionizing, atom is ionizing, it is falling into solution. Electron flows in. Now at the cathode, the copper ion in the solution will take those electrons that are flowing, each will take 2 and then turn to plate, joining and then stick itself on the copper plate. So that's what this whole system stands for. Now, standard electrode potential. This is the potential difference set up between a metallic electrode and a standard hydrogen electrode under standard condition. The potential difference set up between metallic electrode and standard hydrogen electrode under standard condition. So this is what we are talking about there. Now this is a metallic electrode, copper electrode, and here the electrode here is hydrogen, and we are using hydrogen as a standard to measure the potential difference of copper. Now, the reason why hydrogen is used is that at all temperatures, its values remains 0. Now, whatever, this is voltmeter, whatever value that will be coming out here will be the value for the other metallic electrode you are measuring. So you use this setup to measure the potential difference of different elements. Now, if I allow this to run, the electron, we can see that we talked about standard conditions there. Now, the standard conditions are 1 atm pressure, 25 degrees Celsius temperature, and 1 molar solution. So, if you check the pressure here, 1 molar pressure, you see the temperature is what? 25 degrees Celsius, and the solution must have this concentration of this. 0.1 molar solution. Salt bridge must also be there. Then if electrons flow from hydrogen to the metal, the value will be positive. The value that will be read here will be positive. But if I change this metal now, fix another one, and if the electrons, you can see here, electrons are flowing from hydrogen to copper. Now, if I remove copper here and fix zinc, electron will be flowing from zinc to hydrogen. What's the difference? And if it happens that way, the value here will change from positive to negative. You have negative values. Now, the system is built in such a way that if you are using a metal that is below hydrogen in electrochemical series, I have given you electrochemical series, go and watch that video. Check the position of copper, check the position of hydrogen. On that electrochemical series, you see that copper is a little bit above, hydrogen is above hydrogen is above copper on that series. Now, meaning that electron, if you are using two of them, electron will flow from the one above to the one below, which is hydrogen to copper. But if I change copper and fix zinc, zinc is above hydrogen on that series, which means zinc will release electron. Electron will be flowing from zinc to the hydrogen, and the values that will come up here will also change from being positive to negative. So now I have explained all. I said factors affecting the values of electrode potential. 1. Nature of the metals and its ions. 2. Concentration of ions. I've explained all of that. The temperature, when you increase the temperature, it will affect the value that will come up here. Now note, the electrode potential value is 1. Positive. I have explained that. When electron flows from hydrogen to metal electrode. 2. Negative. When it flows from metal electrode to hydrogen electrode. Next is electromotive force of a cell. Electromotive force, EMF, of a cell. So you don't want to call it electromotive force, you can call it EMF of a cell. Now, what is it? This is the potential difference provided by a cell or battery per coulomb of charge passing through it. The unit of electromotive force is what? Volts, and it is always represented with what? V. Now, the calculation of electromotive force of a cell, the formula is given. So use this formula and do any calculation you are seeing coming. Sometimes the values might be negative, whatever thing the value is, use this formula. Now, let's see the question. If electrode potential of copper is plus 0.34 volt and that of zinc is minus 0.76 volt, calculate the EMF of the cell. Calculate the EMF of the cell. Now, they said comment on your answer. Now, the solution. Now, look at the formula here. EMF equal to E cathode minus E anode. So if you check, try to identify which one is cathode and which one is anode. Cathode is this, anode is this smaller value. So now let's substitute them. This will now be equal to 0.34 minus, that minus is from the formula, minus, remember this one also comes with its own formula, minus 0.76. So minus times minus gives you what? Plus. So you have 0.334 plus 0.76. 0.34 the answer is 1.10 volts. Okay, now the is plus 1.10 volts. So now they said you should do what? Comment on your answer. Now, having known, once you see the value being plus, that means that the anode can reduce the cathode. That's what it means. So now I can therefore say that the reaction is spontaneous. The reaction is spontaneous. That's all. You're done with it. You're done with it. So far, so good. I believe you have enjoyed the lesson, and the lesson is impacting positively into your life. Subscribe to the channel, share the teaching, like it, comment, ask question if necessary, and I will do my best to attend to your question. Thank you.